Okay, this is the third lecture in digital signal processing. And in this lecture, we are talking about the image stochastic characterization. The following presentation of the statistical characteristics of the image assume general family of the probability theory, random variable, and stochastic process. And so in this case, we have a function of the image, continuous function, fx, y, and t. This is the space variable, and t is the time variable. In the stochastic process, we describe this f completely by the joint probability P, F1, F2, and so on, if there are many, with the different coordinate X1, X2, and so on, T1, T2, so on. And for all sample of J, and we have the, for instance, for the we have in general, the high order joint probability density image are usually not known, nor are easily modeled. The first order probability density PFD can sometimes be modeled successfully on the basis of the physics of the processor or histogram measurement. For example, the first order probability density of random noise from an electronic sensor is usually well modeled by the Gaussian density such as like this. Okay, let me write for you here. Let me write for you. So this is the image, digital image. Processing. Let me adjust this one. And the probability, this is the stochastic characterization of image with the probability of F1, F2, and with X1, Y1, T1, and so on. For Gaussian noise, probability is f x y t is 1 over root 2 pi. This is the variance sigma 2f x y t and exponential minus f minus eta f. Eta f is the mean value square over to sigma variance f. Here, eta is mean value of image, and sigma square is variance, and this is the probability in this case. The expected value for average is expected of f x y is integral of f x y. I simply write probability density function of f x y df, and variance is f x y is expected value of f x y minus expected value of f x y. It is a square. This is the square of this. So all of this is inside the square. And here we define covariance. I will write covariance for you. Covariance of two image fxy simply, and gxy is expected value of, I write just simply f minus expected value of f multiply by g xy, I abbreviate here, expected value of g. This is the expected value of total is the covariance, and correlation or correlation of g of this one covariance of the g and f is correlation of g. F and g is covariance of f and g divided by the root of variance of each one, f multiplied by variance of g. So this should be remember. So please remember this page as the digital image processing for the third lecture, which is the stochastic process. Okay, let me now change here to the sharing again. So here, what I wrote for you is, this is the, for instance, for, I will not write all of this because maybe it takes time for the, this is for the model of the, first I write for you the, for noise model, this is for noise model. Also with the mean value and variance, Gaussian density function, and another, of course, the probability density of the luminance function must be a one-sided density because the luminance measure is positive. Okay. The other one is the Rayleigh density function. This is the probability density function of the Rayleigh. PF is F divided by alpha exponential alpha squared over 2 alpha squared. And log normal density is the other one in next page. This is log normal. This is logarithm minus the average, and this part. And very simply, I go fast here. Then exponential density is this alpha exponential minus LF, alpha F, and for alpha is the constant on two sides. The Laplace density is this one, alpha over 2 exponential minus alpha F, where alpha is the constant, is selected as a model of the probability density of the difference of the image sum. Finally, uniform density is this one. This is uniform, which is the probability is constant over the f minus pi and pi. This is very in general, of course. And for conditional probability, conditional probability density are also useful for characterization of the stochastic process. Conditional density of an image function valued of x1 and y1 and t1 with the given point of the, for instance, one pixel is x1, y1, another pixel is x2, y2. So conditional is probability given f1, given f2, while the probability of the f1 is the joint probability f1 and f2 divided the probability of f2. This is the in probability, usually you know about this. And higher order conditional density are defined in a similar manner. Another means of the describing of the stochastic process is through the computation of the ensemble average. The first moment of the mean of the image function is defined as eta f, which is expected value of f, which is f multiplied by density function, probability density function f df. E is the expectation operator as defined on the right side. And the second moment of the, which is autocorrelation function, is defined as R, is the multiplication between F and F star, multiplying F and F star. Another one is we can write R as multiplication of F and F star, the joint probability of when F1, F2, dF1, dF2. And also autocovariance of image process is the autocorrelation about the mean. So if you reduce the mean, if the reduction of the mean of both sides, then we obtain the autocovariance K, which is expected value of F minus eta F multiplied by F star minus eta star. So this is the autocovariance. This is variance, second order autocorrelation, and this is the autocovariance. And also variance is defined as sigma F square F as K with X and X. So one pixel and itself. So each pixel is highly correlated with the itself. But the correlation or variation or covariance between this pixel and the nearby pixel gradually decrease as you get the farther pixels. That's why in image compression we use this phenomenon that gradually Nearby pixels are highly correlated. An image process is called stationary in the strict sense if its moments are unaffected by the shift in the space and time. The image process is said to be statistically in wide sense if the mean is constant and autocorrelation depends on the difference in the image. So the mean is constant and the autocorrelation is related or dependent on the difference x1 minus x2, y1 minus y2, t1 minus 2. So the difference between two pixels are important. It doesn't matter where is the position of the coordinate in pixel on the image. In other words, the image autocorrelation is not function of the position or the time. So we have a expected value of f is eta f, and the autocorrelation is r is x minus x2, y minus y minus 2. And autocorrelation expression is written as this one because it is related to the difference. Also, because the symmetry, we have this one, this equation, and then also the for image function f autocorrelation is real even function is the power spectral density, also called power spectral density. The stationary image process is defined as three-dimensional Fourier transform. We defined Fourier transform before, previously, so omega x, omega y, omega f. This large omega means the Fourier transform of the autocorrelation. So it is triple integral of r or exponential minus I omega x t tau x omega y tau y omega t t tau tau. So tau is difference between t1 and t2. In many image systems, the spatial and the time image process are separable on the station correlation function may be like this. Usually it is separable. The spatial geometry is often considered as the product of the xy. So Rxy is this. For completion of simplicity, also for set of manufactured man-made picture, there is often large amount of the horizontal and vertical line images. So the spatial separation approximation by the quite good. So we have them. This equation is good for man-made images, but for natural scene like the jungle on trees or something like that, there is no preferable direction of the correlation. The spatial coordination function tend to be rationally symmetric and not separable. Also, there are different other covariance, autocovariance. This one is the two-dimensional. The autocovariance function for two-dimensional Markov process is this. An image field is often modeled as the sample of the first order Markov process for which the autocorrelation between points on the image field is proportional to their geometrical separation. So this is the Markov process. And this is the energy here. Alpha is a special scaling constant. Markov process separable like this, and the power spectrum is processed like this. I abbreviate this part for you and then jump here. For example, the system output, this is output of the system, the operating mapping of F with the over the F, the mapping F to G. O is the monotonic operator on fxy. So it affected xy and generated g. We know the probability density function of the input. We want to know what is the probability density function of the output. This is very important relation in the stochastic and probability theory. Probability of the output is the probability of the input f divided by the, the derivation of the operator with respect to f, the of to df. And the other momentum here is written, for instance, the expected value. I want to reduce it as fast as possible. This is, for example, if the system operator is additive linear, the mean and system output is, this is in mean value of G is also mean value of this and also operating over the mean value. It can be shown that if the system operator is additive linear and if the system input image field is stationary in the strict sense, the system output is also stationary in the strict sense. Furthermore, if the input is stationary in the wide sense, the output is also wide sense stationary. Consider an additive linear space invariant system whose output is described by the three-dimensional convolution like this. Gxy is f with the impulse response. Also, this is the convolution between f and h, impulse response. And we take the expected value of both sides. And this is the expected value of f is constant, so get out. And then this is the DC of the impulse response, h, the Fourier transform of the impulse response at the zero frequency. This is a function of the linear system evaluation at the origin in the spatial domain, frequency domain. Spatial, this is the space type. And also, following the same technique is easily shown that the autocorrelation function of the system input and output are related by this. So autocorrelation of output and input is related by this. Taking the Fourier transform become like this, Fourier transform of the output, the Fourier transform input, and the impulse response Fourier transform and its complex conjugate. And we can write like this. If I write for you, it takes a lot of time. Anyway, this is the end of this chapter. This chapter is the first chapter of the book. I will show you here the Pratt's. The name of the book is Pratt's Digital Image Processing, written by Pratt. So I can show you this chapter very fast. And just for your convenience, I will try to write the, sorry. Oh, yeah, maybe this chapter started about here, two-dimensional system. And so this is a mathematical model of the two-dimensional system. Image reference, and then this is the continuous image mathematical characteristic. I will, for your reference, I will try to stop sharing here and write for you again the necessary points that I explain in this paragraph for you. I mean, this lecture. I define for you the probability and its joint probability for image. I define for you eta, which is mean value, and sigma, which is variance. Also, expected value of the f is fx y, this function of fxy and df. Variance also can be defined. Var of f is defined by expected value of f minus expected value of f. This is, of course, a square. I forgot to write. Also, covariance between two image f and g is the expected value of the f minus expected value of f multiplied by g expected value of g. And correlation is the covariance of f and g divided by variance f multiplied by variance of g. I jump here for some other, because we have shortage of time. So for independent variance, variable, for independent variable, of course, p probability of fy1 and y2 is probability of y1 probability by y2. And the Rayleigh density, log normal, exponential, two-sided Laplace transform density, and also the conditional probability is important. Conditional density is probability of f1 given f2 is probability of joint f1, f2 divided by probability of f2. This is very important relation in probability. And this I told you that the mean value of f is expected value of f, which is the integral of f probability density functions f df. Also, second moment, right for you. I will try to stop it in very few minutes. Second order, second momentum, autocorrelation is R between x1, y1, t1, and x2, y2, t2, which is the expected value of f to image and f itself complex conjugate. This can be written as a double integral of f and multiplied by f star complex conjugate and joint probability of F1 and F2. dF1, dF2. And autocorrelation, autocovariance is autocorrelation without average. So K is, I write for you simply, EF minus eta F multiplied by F star minus eta F star, which is the mean value of F star. You can write R x1, x2 minus eta F and multiply eta F star. Variance is also is K of X and X. A stationary process, if the process is stationary, then eta is constant. This is very important. And R of x1, x2 is only related to difference of 2 pixels on image. So it is R tau x, tau y, tau t. Also, I write for you a little bit more to finish this part. Of this function, the Fourier transform of the power density function is omega x, omega y, omega t is the Fourier transform triple integral of the autocorrelation tau x, tau y, and tau t multiplied by exponential of minus I omega x tau x plus omega y tau y and omega t tau t and d tau x d tau y d tau t. Next page is like this. This is the power density of image is Fourier transform of autocorrelation. For man-made picture, for man-made image, we have the autocorrelation Rxy, tau x, tau y is multiply of Rx, tau x, and Ry, tau y. So it is horizontal, vertical line more, you can see. But for the natural cell, or natural cell, we have, it is kind of symmetric over there. Like for instance, over there, something like trees and so on. And then it is symmetry and it is not separable. Image process is the Markov process of the first order, and then I wrote for you also a space if the also the ergodicity I forgot to define as the the ergodic process is the process that we have the space average and time average and so the stochastic average, mean the mean value. If these three are equal, then we call the process is ergodic. This is the definition of ergodicity. Also, one important is that if we have a mapping of the O over F, then probability function of the output is probability of the input divided by the differential of the operator with F, absolute value. This is very important relation in probability theory. So remember this. For example, we can also write the autocovariance and so on. The Fourier transform of autocovariance is Fourier transform of G is equal to Fourier transform of the input multiplied by the impulse response Fourier transform. That is the last section that I wrote for you. I explained for you. And this here a little bit takes long, but this this lecture is summarize the stochastic process of the image, this digital image. And thank you very much. This is the third lecture of the series of the digital image processing. Next, I will talk about more other items such as how human eyes is sensitive to the sensitivity of the image file and more the structure of the image will be discussed there. And here I will stop here and thank you very much.